So here's a quick discussion of theorem 1.5.1, presented as a two-part theorem. So first, A is just any m by n matrix. Then, first of all, the matrix equation AX equals 0 will always have what's called the trivial solution, which is x equals 0. And let's talk just about that one. Won't even get into B first. But so AX equals 0 always has a trivial solution, x equals 0, because whatever your matrix A is, if you multiply by the 0 vector, so this is a discussion of part A, 0 vector is so a vector with zeros for all of its entries, right? And when you do a matrix times a vector, remember that one way to look at that is the first entry in the vector, so that's all the entries are going to be 0, times the first column of A, which I'm going to write that as A1, plus the next entry in this vector, so 0, times the second column of this matrix A. So I'm going to call that A2. So this A1 right here represents the first column of A, right? This is the way that product matrix times a vector, that product was defined. It was this entry times first column, second entry times second column, and so on until we get to the last column, which if this is m by n, so that's m rows and n columns. So eventually you'll have the nth column here. But if it's each of those columns times the scalar 0, then yeah, definitely the result is going to be just the 0 vector. You're going to have all zeros across the board. So we're guaranteed that AX equals 0, it's always going to have at least one solution, which is the trivial solution. Now remember, so getting into part B here, we said that so for a system of linear equations, there's three ways that it can play out. It can have a single solution, it can have no solution, or it can have infinitely many. There's three possibilities. So it's either one solution, 0 solutions, or infinitely many. You don't get a system with two solutions. That doesn't happen. Now, we just said in part A that AX equals 0 always has the trivial solution. So it's always got at least one. So it's not going to be an inconsistent system ever. So it's got at least one solution. If it has more than one solution, so if it has what we call a nontrivial solution, then it's got to have infinitely many. And so that actually kind of gets at the reasoning behind part B. Now, when you see if and only if in a theorem in mathematics, that means that the logic flows both ways. So my argument right now is, all right, let's prove that the logic flows this way. Let's assume that AX equals 0 has non-trivial solutions, or let's say just a non-trivial solution. It's got some solution that's not x equals 0. I'm going to abbreviate solution there. But we know that it definitely does have the solution x equals 0. Just here we're saying it also has some solution where x is not equal to 0. Okay, well, if we're talking about more than one solution, then we're talking about infinitely many. So based on that, we can say that this equation has infinitely many solutions if it's got more than one. By that theorem back in the first section that says these systems of linear equations have 0 solutions, 1 solution, or infinitely many. So once we know we're more than one, we know we're at infinitely many. Okay, infinitely many solutions, which means it's a dependent system, and it has a free variable. Okay, so that's the logic explaining why, okay, if it has non-trivial solutions, then it has to have free variables. Okay, but I said this if and only if implies the logic goes both ways. So what if we, so draw a line here. What if we start at the other end? Assume that the system AX equals 0 has free variables. Well, if it has free variables, I mean, say x3 is free, like in one of the previous videos that I put up in this section. If x3 is a free variable, then that means that we can certainly, there are solutions where x3 does not equal 0 because we can make x3 whatever we want. So that implies that there are solutions, infinitely many in fact, solutions where whatever your free variable is, and I'm just pretending like it's x3, does not equal 0. We could find a solution when x3 equals 1, and when x3 equals 2, and when x3 equals 3. But so those would all be non-trivial solutions, because a trivial solution is just the 0 vector, the 0, 0, 0, 0, 0, vector whose entries are all 0. If you have a free variable, then that free variable certainly doesn't have to be 0 in order for you to build a solution off of that. So there are definitely non-trivial solutions. So I just want to talk through all the logic connecting the dots in this theorem here.